Today we're going to cover the governing equations of statics, free body diagrams, and then run through an example. Can you tell me what statutes, and standards have in common? They stay put, they're stationary, they're stable, they're static, and that's just an old prefix that means to stand firm. In other words, their acceleration vector is equal to 0. Let's take a look at what that means in the context of Newton's second law. So if your acceleration vector is equal to 0, then mass multiplied by your acceleration vector is equal to 0. And we remember from Newton's second law that mass multiplied by acceleration is force. So when your forces are equal to 0, more specifically, the sum of all your forces in the x direction, the sum of all your forces in the y direction, and the sum of all your forces in the z direction equals 0, you have static conditions. Similarly, when the sum of the moments about the x-axis, the sum of the moments about the y-axis, and the sum of the moments about the z-axis are 0, you have static conditions. Now remember, a moment is just a force multiplied by a distance. And under these conditions, we can model just about any structure, whether it's a crossbow, a truck, the walking beam of a pump jack, a catapult, a wrench, or a hand drill. By using free body diagrams, we can take relatively complex structures and break them into pieces and look at those pieces in isolation. And by doing so, we can analyze their internal and external loadings, which result in different stresses. And as engineers, we can look at where and when these structures might fail. And in the design phase, we can avoid it. Dr. Kennedy defines free body diagrams as a sketch of the entire structure or part of a structure that has been cut free of its attachment points to its surroundings. If you have a structure and you want to look at a piece of it in isolation, you have to break it free from its surroundings. That's why it's called a free body diagram. And wherever it connects to its surroundings, you have to replace that connection with some kind of support condition, forces, moments, or not, depending on how it's connected. So let's look at some of those standard support conditions. So let's say we have this wild and crazy structure. Maybe it's a jungle gym. If we were to look at one little piece of it, all right, let's blow this up, where it connects with the rest of the structure has to be defined. It's now a free body diagram. We're modeling just that one piece, but we still have to define how exactly does it interact with the rest of its environment. And so that's what we call a support condition. In this case, if it's a jungle gym, then that's just a fixed support condition. And that would be the entire free body diagram, but it's also good to have a little reference frame, which is arbitrary and up to you as the modeler. Let's review 4 common support conditions. The attachment points will be on the left, and the member will be on the right. And let's just ignore the rest. We'll look at the attachment point on the left for now. There's fixed, free, pinned, and pinned with a roller. And these are simplifications. What this is essentially saying is that when this body is attached to the rest of the structure, its movement in the x direction, the y direction, and its rotation about the z direction, pointing out of the page, is inhibited. So in the free body diagram, we'll need to put a reactionary force in the x direction, a reactionary force in the y direction, and a reactionary moment about the z-axis at that attachment point. In the case of the free attachment, that's not really an attachment because there is no attachment. And so we don't put any reactionary forces. In the case of a pin attachment point, it's allowed to rotate, but not move in the x or y direction. So there is no reactionary moment, because if there were a moment, it would just rotate. So all we have is a reactionary force in the x direction and a reactionary force in the y direction. Finally, the pin with roller connection enables rotation and translation in the x direction. So all we have is a reactionary force in the y direction. Let's say, for example, we have a simply supported beam. Simply supported just means we have a pin connection at one end with a degree of freedom in the x direction, assuming x is horizontal. And at the other end, we just have a pure pin connection that restricts motion in the x and y directions. Let's say we have a 1,000-pound force acting on this little nub here. This is not drawn to scale. The force is 5 inches away from one end and 20 inches away from the other. And it's 5 inches top to bottom. So with this problem setup, we might be asked any number of things, or we might need to find out any number of things. Typically, we will need to discover the reactionary forces at the attachment points, because when we know those values, we can determine the internal loading. And with the internal loading, we can determine the resultant stresses inside the member, and that will tell us if it will break or not. So in order to find the reactionary forces, step number 1 is to draw your free body diagram. Not great, but not bad. In drawing a free body diagram, it can be helpful to use some level of terminology. What do we call this force here? Well, let's call this point A, we can call this point B, call this point C, call this point D. So we'll just call this force in the y direction at C. And so over here, we can have force in the y direction at A, and force in the x direction at A. And then we have our 1,000 pounds. And then the dimensions hold true, and there's your free body diagram. Now, in order to solve for these reactionary forces, we apply Newton's laws. So that some of the forces in the x direction, remember we defined x as positive when the force is pointing to the right. So we have 1,000 pounds plus the force in the x direction at A equals 0. So we simply solve for F sub xa, and we get F sub xa equals negative 1,000 pounds of force. Negative indicating it's going in the opposite direction of our reference frame. For some of the forces in the y direction, we have the force in the y direction at A plus the force in the y direction at C, and that equals 0. We don't have enough information to solve for either of these forces right now, but we still have another equation we can apply. Consider the sum of the moments about the z-axis. Before we sum moments, we need to determine some arbitrary point that we're going to sum moments about in the xy plane. I'm just going to say A, so we'll sum moments about this point right here, but we would get the same result if you sum moments about B, or C, or D. Now, sign convention is arbitrary, but it's customary to say a counterclockwise moment is positive. So if we're looking at this, remember, moment is force times a distance, so the force in the y direction at A and the force in the x direction at A are not considered because they go right through point A. And so our D would be 0, and moment equals F times D, force times distance. So all we care about are these two. So here we have a negative 1,000 pounds because it's going clockwise, multiplied by the distance 5 inches, plus the force in the y direction at C multiplied by 25 inches. And we can solve for FYC now, because this equals 0. 1,000 times 5 is 5,000, and we add it to the other side, so it's actually positive 5,000 now. It was negative. Then we divide it by 25, and we get 200 pounds. Now we can come back to this equation from earlier, and we know that this is 200 pounds, so this must be negative 200 pounds in order to get 0. So summarizing all that, we have the force in the x direction at A is 0. The force in the y direction at A is negative 200. The force in the y direction at C is 200 pounds. And that's all for now. Next time, instead of covering point loads, we'll cover distributed loads, when the forces are not so simple to determine. If you join me, I will be ecstatic.